Hello everyone and welcome back. In today's video, we're going to get started building up some of the tools and techniques that are used to solve second order differential equations. Differential equations that contain a second derivative. And to that end, the topic that we need to talk about today is something that is called linear independence of functions. And before we can talk about linear independence of functions, I need to introduce a concept called a linear combination. So what's a linear combination? When someone talks about a combination that is linear, they're talking about a combination that is created using only constant multiples, sums, and differences. So for example, if somebody wants to create linear combinations of the functions sine and cosine, they can combine sine and cosine using constant multiples, sums, differences, and nothing else. So for example, I could combine 5 times sine plus 4 times cosine. This would be a linear combination because I've combined these two functions using just constant multiples and, in this case, an addition. It could also be sine of x minus 7 times cosine of x. Here I'm combining them using constant multiples and differences. I could do cosine x plus 1/2 sine of x. Just constant multiples and sums. So each of these would count as a linear combination because I've combined these functions using only constant multiples, sums, and differences. Now, by contrast, here are some combinations of sine and cosine that are not linear. I am not, for example, allowed to multiply these functions together. That is not permitted. I am not, for example, allowed to divide these functions. That is not permitted. I am not, for example, allowed to have any of these functions raised to a power. Exponents are not permitted. So anything like this, any combination of sine and cosine that is created by any action other than simple constant multiples, simple addition, and simple differences, these are not considered linear combinations. Let me do another example. Here we have the functions x, e to the x, and e to the 2x. So here are some examples of linear combinations of those three functions. I could do 3x plus 5 e to the x minus 4 e to the 2x. This is a linear combination of these functions because it's just constant multiples, addition, and subtraction. I could do 4x plus 7 e to the x plus 18 e to the 2x. This is a linear combination of these functions. But I am not, for example, once again, allowed to do any multiplication of these functions. This would not be considered linear. I'm not allowed to do any division of these functions. This would not be considered linear. So that's what a linear combination is. A linear combination of functions is obtained by just adding, subtracting, and applying constant multiples. Now, having established that, I can give the most important definition for today, which is called linear independence. A collection of functions is called linearly independent if none of the functions in the collection can be obtained by linearly combining the other functions in the collection. A collection of functions is called linearly independent if none of the functions in the collection is a linear combination of the other functions in the collection. So let me give you an example of a collection of functions that's not linearly independent. This collection of functions is not linearly independent because I claim one of these functions can be obtained by linearly combining the others. Now, what's coming to mind for me right now is that if I construct the sum of the functions sine squared and cosine squared, this is a linear combination of sine squared and cosine squared because I have combined those two functions using only addition. But this linear combination of sine squared and cosine squared is equivalent to the third function in my collection, 1. So here I have obtained the first function of my collection via a linear combination of the other two, and that means that this collection of functions is not linearly independent. Now, let me try and capture in plain terms what linear independence is saying to us. If you have a collection of functions that is linearly independent, then that collection of functions does not have really any redundancy inside of it. By contrast, a collection that is not linearly independent has a redundant function in there somewhere. For example, up here, with this collection of functions, the constant function 1, the function sine squared, and the function cosine squared, we really don't need to have the function 1 in this collection because we can create one just by combining sine squared and cosine squared. So the way that I like to think about it is kind of like when you're mixing colors for painting. When you have a linearly independent collection of functions, that's kind of like having all primary colors. You don't have any colors in your collection that you can create by mixing the other colors in your palette. Here, I can create one by mixing together sine and cosine. So this collection, as it stands, has a color in it that's not a primary color. It's a secondary color that can be found by mixing together the other two. In certain situations, it may be difficult to just look at a collection of functions and see whether there is redundancy in the collection or not. In this case, we had access to the Pythagorean identity, which made it very easy to see the redundancy, relatively speaking. But in more exotic cases, it may be very hard to just look at the collection and understand what's going on. So in this part of the video, we're going to introduce a tool that is used to calculate to see more clearly if your functions are independent or not. And the tool we're going to use to check for independence is called the Wronskian. So the Wronskian, if you have a collection of functions, let me just generically call them y1 through y sub n, the Wronskian is a matrix determinant. And so I am going to write vertical bars here to capture that it's the determinant of a matrix. The determinant of what matrix? Well, the first row of your matrix is going to be filled with all the functions in your collection. The second row in the matrix is going to be filled with the derivatives of the functions in your collection. The third row is going to be filled with the second derivatives of all the functions in your collection. And you keep going row by row, taking more and more derivatives until the matrix is square. So to give you an example, if you just have two functions in your collection, the Wronskian would be the 2 by 2 matrix determinant that had the original functions in there and their derivatives in there. If you have a collection of 3 functions, then the Wronskian is going to be the determinant of a 3 by 3 matrix, 3 functions, and 3 rows, the original functions, the first derivatives, and then the second derivatives. And this will be the situation that we focused on most in this class, just a 2 by 2 Wronskian and a 3 by 3 Wronskian. Now here is the result that connects the Wronskian to the idea of linear independence from earlier. If you have a collection of functions, you set up the Wronskian for that collection, and you find that matrix determinant. If the result of that calculation is equal to 0, that is the indicator that the functions in your collection are not independent. If your Wronskian equals 0, then somewhere in your collection is a function that is redundant and a function that can be created by combining the others in that collection. By contrast, if you calculate your Wronskian and it's anything other than exactly 0, then you can rest assured that your collection of functions has no redundancy in it. Your collection of functions is independent in this case. So let's practice using the Wronskian to check whether a pair of functions is linearly independent or not. And in particular, let's use the Wronskian to prove that if we have two power functions, x to the power n and x to the power m, that these two functions form a linearly independent collection. To that end, what I'm going to do is I am going to list my two functions, and I'm going to write down what the derivatives of those functions would be. Using the power rule, the first derivative sees the exponent come down to the front, and then the exponent is decreased by 1 unit. And then, likewise, for the other power function, the exponent m comes down to the front, and then the exponent is decreased by 1 unit. So then I'm going to go ahead and set up my Wronskian matrix, which in my case has 2 rows for each of my 2 functions, as well as the derivatives of each of those 2 functions. This forms a square matrix. And so I can calculate the determinant of that matrix using the standard 2 by 2 matrix determinant formula, which says start by taking the product of the 2 entries on the main diagonal, x to the n times mx to the m minus 1, and then subtract the product on the off diagonal, nx to the n minus 1 times x to the power m. Now, using the exponent properties, if I simplify that, I get m x to the power n plus m minus 1, combining those two exponents on x. And in the back, I have n x to the m plus n minus 1. And in fact, I'll write that in the other order. So we can really see that in this case, the two exponents on x are the same. And we get, after factoring, m minus n x to the power n plus m minus 1. So the question is this equal to the zero function or not? If this is equal to 0 for all values of x, then that is a sign that these two functions are linearly dependent. However, if this expression is not equal to the zero function, if there is even a single value of x at which this quantity is non-zero, then the Wronski is saying that these two functions are independent. Now, the key to resolving that question lies right here. They're saying to us that we should assume that the exponent called n and the exponent called m are not the same, which means that if we subtract them, as we have down here, this guy is non-zero. As a result, we know that there's going to be at least one value of x that causes this quantity not to become 0 in the end. For example, if x is 1, then this is not equal to 0 because I would have 1 times m minus n. So that would be a non-zero product. As a result, we can say that this is not equal to the 0 function. This is not equal to 0 at all values of x, and therefore, the Wronskian proves that x to the power n and x to the power m are independent in this case, where the two exponents are different. One more time, just for the practice, let's use the Wronskian to show that if the number a and the number b are not exactly equal, then the functions e to the ax and e to the bx are linearly independent. Once again, all I have to do is throw these functions into the Wronskian and show that the result of the Wronskian is not equal to the 0 function. So I take my expression e to the ax, and I take its first derivative using chain rule, giving me a e to the ax. And for the second function, e to the bx, its derivative would be b e to the bx, for that same reason, for that same chain rule. So I throw these functions into the Wronskian matrix, and I calculate that determinant, and I find e to the ax times b e to the bx minus a e to the ax times e to the bx. And using the exponent properties, we get b e to the ax plus bx minus a e to the ax plus bx. So once again, we have this difference b minus a times this function, in this case, this exponential function. And I'm asking the question, is this guy equal to 0 for all values of x? Is this guy equal to the 0 function? And once again, that is determined entirely what b minus a is doing. If b minus a is 0, then the whole thing becomes 0. If b minus a is not 0, then the whole thing is not equal to the 0 function. So to resolve that, I'm going to go back to the question and remember that we are allowed to assume that A and B are not equal, which means that when we subtract them, this quantity is not 0, which means that this Wronskian is not equal to the 0 function. Thus, the Wronskian proves that e to the ax and e to the bx are linearly independent. There's no redundancy in that collection.